say?
No, it didn't say.
Okay.
In the past, some have done double columns, and some have not done double columns. So, okay, guys, good morning. Let's get started. Next week, we're doing the shaken, not stirred in lab, which is a substitution reaction. Group lab report due next week when you come to lab. Any questions about group lab report? Okay, we'll begin with Diels-Alder here. Before you do that, any questions about resonance or Diene reactions? Both of those packets had questions to work. Any questions about those problems? Resonance or Diene reactions? No? Okay, let's begin with Diels-Alder. Diels-Alder, we also have regioselectivity. We talked about stereoselectivity. This is an example here. These two can zip together. 4 plus 2 is 6. If these were like this and they zip together, boom, 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 this would give which one of these? Well, the methoxy's down. We label this 1, 2, 3, 4. Methoxy's in the 4, 5, and 6. 4 is bonding to 5. 1, 2, 3, 4, 5, 6. 4 bonding to 5. Well, 5 doesn't have that group. So you see it's like this. How would you get that other product? The other product comes from this being flipped over and drawn like this. And if you draw this the same way, if you zip it together like this, well, I should have turned this over. Basically, 4 and 5, these two carbons are bonded together, but these two carbons have substituents. That would be this, where these two carbons have substituents. It's just flipped up. So which way is this going to zip together? This is regiochemistry. Because these are regioisomers. Now, regioisomers, as we learned 6 weeks ago, are constitutional isomers that come in the context of a reaction. Constitutional isomers. Which do you get? Well, you're going to get one very selectively. How do you judge this? You've got to look at the polarization of your pi bonds. Let's first look at the dienophile. It's the easiest. As you remember from the previous page, these typically have electron withdrawing groups on them. That's to polarize the alkene portion, the reactive portion. We've got here, but that's more than just a dipole. We can also do resonance. And we can move these electrons up. And if you start doing resonance here, move the electrons up, polarize the pi bond. We did this 2 lectures ago. That gives this resonance structure here. Well, now we can do resonance involving the pi bond, and we can just windshield wiper this over, and we can get a resonance structure that looks like pi bond here now plus here. And these are all resonance structures. Now the true structure is a blend, and so we have oxygen. What's the average of double, single, single? Well, it's somewhere between 1 and 2, okay? What's the blend of single, single, but double? Somewhere between. What's the blend of single, double, double? Somewhere in between, okay? This is your hybrid. You've got pi bonding all through here. It's all through there. 1, 2, 3, 5 p orbitals, and that water is spread out all through there. Okay? How about charge? Neutral, negative, negative. Partial negative. Importantly though, on your alkene, which alkene carbon? Coming off of a carbonyl, the first carbon is called alpha, the second carbon is called beta. Oh, we heard that yesterday, right? Which carbon has partial positive charge?
The bottom.
How'd you know that? Because you looked at the resonance structures. Right? Look at the alpha carbon. Neutral, neutral, neutral. Don't see any charge. How about the beta carbon? Neutral, neutral. Ah, it's got a little positive character. Partial positive. How about the carbonyl carbon? Neutral, positive. Okay? Here's your true structure. Beta carbon is electron poor. Or another way to say that is electrophilic. Now something that's electron poor is going to like electrons. That's important. The beta carbon is partial positive. But that's consistent with any of these dienophiles. This general type of compound, and we'll see much more in organic too, is called an alpha beta unsaturated carbonyl compound. Alpha beta unsaturated. What does that mean? That means between the alpha and beta position we have unsaturation. Is it a pi bond degree of unsaturation? Okay. That's an alpha beta unsaturated carbonyl compound. These and compounds like them, the beta carbon is electrophilic. And we can hopefully understand that by looking at the resonance of this. Also, which is governed largely by the polarization of the oxygen, and we can start doing resonance structures to coincide with that polarization. So, partial positive, that's what we identified there. And typically your dienophile has a partial positive. Now this guy's going to have a partial negative. We got to identify where it is. The question is it 1 or 4? If we number this 4, 5, and 6. Which one? 1 or 4 is partial negative. Because once we identify which is partial negative, then it's easy because the partial negative carbon is going to end up bonding to the partial positive carbon. So which one bonds to this carbon over here, 1 or 4? Before I erase this, any questions about the alpha beta unsaturated carbonyl compound and seeing the resonance and identifying that as partial plus? Okay, draw resonance of this. Neutral compound. Where do you want to start when you do resonance? It's listed somewhere in the notes, probably on the golden rules of resonance. Also, when we did this, it's probably listed in bold. Lone pair. Okay, you should be able to do resonance of this. Or resonance structure. Lone pair is a great place to start. Okay, we can move these in and move these out, right? In and out. Everybody's been practicing resonance structures, right? What does that give? Get this resonance structure here. We can keep going. These electrons can come here. These can come out. Does that look right? What does the hybrid look like? Well, you got partial bonding all through here. What's the charge on oxygen? Partial positive. Where are the other partial well charges? The other is negative. We have partial negative where? Here? And where? And there? There's our true structure, and if you could take a snapshot of it, you would have sort of high electron density on that carbon, this carbon, and actually some partial positive on the oxygen. So the water, the electrons are not truly equally distributed. There's more electrons on this carbon and this carbon compared to that one and that one. There's electron density. Okay, but of carbons 1 and 4, which one is partial minus? 1. 1 or 4? Not up there, right? There you go. Partial minus. Now this could vary. This is always consistent, beta carbon. This can vary, depending on where the group is. Okay, that can vary. So that's partial minus, this is partial plus. You want these two to bond together. So what do we need to do? If that's 1, 4, 5, and 6, 1 and 5 are going to be bonded together. Basically, we need to flip one over. You can flip this over. Let's flip this over and make it like this. O-methyl. O-methyl. That carbon is partial negative. That carbon is partial plus. These two are going to bond together, zip together like this. And which one do we get? Yes, you get that one. Not that one. Because when these approach each other, the partial negative and partial plus, which is truly there, they're going to bring it together and make the attraction come together and make the bonding then happen. Now, what about stereochemistry? You're not going to be able to tell the relative stereochemistry between here and here. Because the only thing we looked at, you can tell there, relative there, or relative here. But we did not look at telling relative between one and another. So I'm just going to show that generic. How many total stereoisomers possible for this compound? 4? Okay, one below. There's one below, and then there's one down here. Actually, I'll let you do both of them on your own. It's the same idea of what we just did. Okay? And I'll answer them in class on Wednesday or later. It's the same idea. Resonance structures. Hopefully you already know over here which carbon of the alkene is partial positive. Alpha or beta? Beta. Beta, right? Okay, next page is the answers to the dienes. There were no questions about those answers? So one of these topics is a little odd. I thought there'd be a question about it. Nope. Here's a synthesis of Tamiflu. Tamiflu, used to treat the flu. The first step in making Tamiflu is a Diels-Alder reaction. This diene with the oxygen bridge reacting with that, it's actually an alpha-beta unsaturated carbonyl compound. They use zinc chloride as a Lewis acid catalyst. That can be done. We really didn't talk about how a catalyst could act. They get this product with a bridge. Exo versus endo, that's diastereomers. But then they're off. Ultimately, this oxygen bridge is opened up. And only the 6-member ring is there. This oxygen, which now has this group here, used to be bridged over here. Way back up there. But then it disconnected from here. And then after it disconnected, they put this group on. You can look through there. Most of that chemistry is pretty advanced. We're not going to see, except for here. This is a mesylate. We will see that, but we'll mainly see tosylates. Okay? This is something we're going to see in another week or two. The rest is kind of advanced chemistry, but it may be similar to other stuff that may be of interest. On the back, Diels-Alder again is a general type of what type of reaction? Yeah, it's a diene reaction with a dienophile. It's a type of pericyclic reaction that was said on the intro page. Pericyclic reaction is a reaction that involves a cyclic transition state. Diels-Alder is just one type. There's actually 3 subtypes, and then Diels-Alder is a type of one of those. The subtype is a cycloaddition. Because when we do a Diels-Alder, we're taking 2 molecules and we're adding them together. And we're making a ring with the cyclic. It's called a cycloaddition. Cycloaddition is a type of pericyclic reaction. There's lots of reactions that are cyclic transition states. Prostaglandin synthesis in your body. Prostaglandins are involved with things like pain, inflammation, etc. Aspirin. How does aspirin act? It inhibits the cyclooxygenase enzyme. What does this enzyme do? It converts arachidonic acid to this precursor, PGG2. Where arachidonic acid reacts with oxygen, this enzyme makes this happen. Aspirin inhibits this enzyme. It inhibits the synthesis of this. Thus, it inhibits the synthesis of these things, and you don't get as much inflammation or pain or some things. Well, look at this reaction going from arachidonic acid to this with oxygen. What's going on? It's not a Diels-Alder, but it's somewhat similar. If we draw oxygen here as a double bonded O, almost like an alkene, but it's oxygen, double bond oxygen. And if these electrons attack the oxygen, and if these electrons attack here, and if these electrons move up there to replace what went out, what do you get? You get the product shown if you can follow the arrows, and hopefully you can, because they're important reports. Now, it's not exactly a Diels-Alder, but this is almost kind of like a diene, and this is almost like an alkene. it's not a conjugated diene, so it's not exactly a Diels-Alder. But it is a pericyclic reaction. And that's how you get to this. An octane is reacting here. And from there, ultimately, this this peroxide linkage is broken. But ultimately, these prostaglandins tend to have OH groups on there where these used to be bonded, but then they're broken and then they become just oxygens in the molecule. Okay. Now, prostaglandins you may or may not see in other courses, but if you go to medical school, you will certainly cover prostaglandins and stuff. And look at all this chemistry. Okay, any questions about Diels-Alder? Okay, that was the opening act. Move on to the main show today. Substitution reactions. Very important chemistry. Synthesis of Allegra. Actually, the last two steps were in the group lab intro page. Involve hydration of an alkyne. But the previous initial steps are also shown. And it does involve a substitution reaction. Also a mesylate again. Mesylate, just like on the previous page. Here, the nitrogen, this nitrogen here replaces the mesylate group. So now on this carbon is now the nitrogen instead of the O-mesylate. It's a replacement reaction. But in organic we call it substitution reaction. Now it's different from addition, because when we did addition, we didn't replace anything, we just added. Substitution. And that's a standard type. Now mechanism is called SN2. We'll see two mechanisms, SN1 and SN2. Hopefully when we go through this, you'll be able to quickly understand why this is an SN2 and not SN1. You'll be able to show the mechanism for this, etc., etc. There will be stereochemistry involved in these reactions. But it won't be anything new, because when you attack a cation, which side do you attack from? No, when you attack a cation, which side do you attack from? Anybody? I'll assume you all know, but you're just not willing to say. I gave you a single handout about the two. When you attack a carbon with a leaving group, you attack. Okay? All right. Now, things we learned 3 or 4 weeks ago are going to be very important. Right? So you guys are probably used to Gen Chem, where 3 or 4 weeks ago you're like, I totally forget about that stuff. Right? This is not Gen Chem. It's organic. Stereochemistry. Everybody's really ready to deal with stereochemistry, right? Because now we're taking basic stuff and we're going to start building. But I can't really teach you stereochemistry as we go along. Okay. That's opening page. Next page is reactions. You can start looking at these and be trying to start working these. Okay, let's look at this general line reaction. We take this substrate, it's an sp3 carbon with an X group. What is X? It's going to be called a leaving group, right? I say Lg. Okay? We're going to have a nucleophile. Nucleophile, typically we're going to have a lone pair. In the chemistry, the nucleophile is going to replace the leaving group. Now the nucleophile is bonded to the carbon, and the leaving group has left. That's what leaving groups do, they leave. Now the leaving group must be electronegative enough to take on an extra lone pair. Now I'm not showing complete up here. I don't know how many lone pairs this has, but when it leaves, it now gets another lone pair. Now if it had 2 here, it's now going to have 3. Okay? That's really nothing to learn. If you know structure, you know it's going to be there. This is a simple substitution reaction. Now, what type of carbon did this take place at? It took place here. That's where the substitute. The leaving group is on that carbon. Then the nucleophile. What type of carbon is it? I would check the headings, because usually my headings are like, this is neon. What type of carbon? Tetrahedral. Now in a week, I'm going to have to remind you that it's tetrahedral. Okay. Leaving group. What's the best leaving groups? Halogen. Of the halogens, which one's best? Iodine. So, what about size? Which halogens are best? No, the larger ones. That's what this implies. I mean, if iodine is the best, we know iodine's bigger, so we can say that the bigger is better. It really just has to do with stability. Which is more stable, I minus or F minus? I minus, right? Go back to week 2. So I minus is going to be more willing to leave and become just I minus. Now, I'm not showing any charge up there. I'm not showing any charge. It's very generic. Let's look at more of a precise example. What if we take this and make the leaving group a bromine? Nucleophile, how about hydroxide? These should fit the general trend. What has happened here? Hydroxide is now bonded to the carbon and the bromine has left. So that's a substitution out of tetrahedral carbon. Now here we have charges because the nucleophile is negative. And the bromine has 3 lone pairs here, but when it leaves, it actually takes on these electrons and becomes a 4th lone pair. And lo and behold, that's minus, right? You always have to show perfect charge. That should be nothing new. Anytime there's a charge, you need to show it. It's part of a mechanism. Okay, what's the mechanism for this? Is it magic, or should we be able to show some arrow movement? Well, we should be able to show the arrow movement. And there's going to be, as we go through here, 2 different mechanisms. Now, the majority of instructors will do one mechanism and concentrate on it for 2 weeks and then for 3 days. And then we'll move on to the next mechanism. But I'm going to show them both right now. And we're going to start comparing them, as opposed to just focusing on one and then moving to the other and keeping it compartmentalized and not being able to compare. Let's do them both. But then we need to look at it and say which one makes more sense. Because one is going to make reasonable sense, the other one's going to look very suspicious, like, why are we doing that? But both of them will operate, it just is going to depend on the actual substrates. Okay, the first one I'm going to show is called SN1. which stands for substitution binucleophile or substitution nucleophilic unimolecular. What does that mean? Let's see. SN1. Okay. Mechanism needs to show all bonds breaking and forming electron movement. Obviously, the carbon-bromine bond's got to break. Obviously, this has got a bond here. How do we show it? What sequence do we show it? All at once? What? Okay. Anybody propose the first step? What can we show happening first?
So the oxygen binding to the
What, this just doing this?
Yeah.
That's it?
Okay, that's the first step.
Okay, well, what does that give? You're just showing that bonding there. How many H's on the carbon?
2.
2. So you just want to. How many bonds does this carbon have? 5. Carbon doesn't make 5 bonds. What you want to try? These electrons doing this? What would that give? Somebody said something. Well, it would give, and what would the, so you want to break the sigma bond. And the bromine would then be what? What does this arrow mean to us?
Face apart.
Electrons move on to bromine. And what is that? Well, we are trying to form that. That's reasonable. What is this?
Positive.
How many H's there?
2.
2. What is this? It's plus. Okay, is this reasonable? What is it? What could? Yes, it's one of these mechanisms. What do you want to call this process? Give us some terminology so tonight we can say, hey, remember that first step when we, what do we do? Ionize. The bromine just ionized off. Can a bromine just leave a carbon and leave a plus behind? What happens when you put HBr in water? What does it do? It ionizes. It just leaves the H, and you get H plus what? Br minus. It ionizes. And you did this in Gen Chem, right? And then you talked about what's going to promote ionization. What type of solvent? What kind of solvent will support these ions? Polar salt, like water. Put HBr in water, it ionizes. What if you put HBr in hexane? Will it ionize? It won't. All that was covered in Gen Chem, right? Okay. This is just ionization to make not an H plus, but a carbon plus. Yes, ionization will be very common. Good leaving groups can just leave. That's what they're known to do. That's what we call them leaving groups. But is anybody suspicious about what we just made? What type of cation did we make? Primary. You like primary cations?
No.
Yeah, it's a primary cation. But that's okay. This is the first step of SN1. We're doing an SN1 here. Okay. How can we finish it off? What do we need to do next? Now these electrons could come here and attack. Is that reasonable? Would these electrons be attracted to that plus?
Yes.
What would this give?
That.
Yes, there you go. Br minus is made, and this comes from, how many steps did we do?
2.
We did an ionization. And then what do you want to call this here? Just describe it.
Synthesis.
That's a nucleophile, right? Nucleophilic addition
Get him.
to what? To the carbocation? I mean, that's what we did, but describing it in your head helps you solidify what just happened, right? Okay. This is an SN1. We'll do the mechanism differently down here. Before we do, let's do a reaction coordinate diagram for this. Okay? I'm not going to label the axes, you know, energy, reaction progress, right? You should be able to do all this. What do we start with? Let's just put up the organic substrate. Some relative energy. Do we have an intermediate? What is the intermediate? Carbocation. Is it higher or lower than this? Yes. Carbocation. Then we go to what? Product. Where's product? Now here it's not intuitive because we're just one signal bond to another signal bond. It's not as easy to say. So I'm just going to show it about the same level. Okay, when we go here, is there a transition state or what? Yeah, transition state. And when we come here, how big of a transition state? Not much. Doesn't take much energy to fall downhill. Okay, of the two steps, which one should be rate determined? First one, formation of the carbocation. This step is thus what, relatively? Fast. That is, if you wanted to speed up this reaction, which step would you want to speed up? First one. You speed this up, it ain't going to do anything for you. It's like bottleneck getting out of this room. You're all going to quickly get over there, but then it's going to take time to get out the door, especially if what if it was real narrow. If we wanted to speed all you guys getting up, I wouldn't say, hey, you got to rush over there quicker. It's not going to do you any good. You got to get you out the door quick. That's the step you got to worry about improving. Okay. Of the two substrates, which ones are involved in the rate determining step? One, both, none? Question, is the bromide involved in the rate determining step? The alkyl bromide? Yeah, I mean, fine, I don't know what it's doing. It must be involved. Is the hydroxide involved in the rate determining step? No, it's not. Only one of the substrates was. Only one of the substrates is involved in the rate determining step. That's why it's called SN1. That's also known as unimolecular. Only one molecule was involved in the rate determining step. Just ionization. This didn't have anything to do with the ionization. The ionization was the rate determining step. How can we make this reaction faster? Do we need to worry about this step over here? No, here. How can we make this faster? Well, it's sort of where you're going at question. But if this was secondary cation, would it be higher or lower than this?
Lower.
Be lower. And if this was lower, would this reaction be faster?
Yeah.
That'd be easier to get to. Yeah. So keep that type of thing in mind. We'll come back here and probably revisit that, but you need to be able to assess your reaction coordinate diagram. Great. Let's look at another mechanism. Let's look at what is called SN2. And what might the 2 mean? Both? Yeah, they're both going to be involved in the rate determining step. Okay, what's another way to show this? What's another mechanism? So we don't want to just have it bonded here and make a pentacoordinate carbon. Pentacoordinate carbons don't exist. We don't want this to ionize off because we don't want to repeat the mechanism we did up there. What's a third way? What's another way? Anybody?
The OH attack the backside of the carbon and the bromine leaving at the same time.
You can do that? Have we ever attacked a carbon and kicked off the leaving group? Yeah, we did it many times, like when you attack bromonium and kick off the BR. Yeah, we've done it. Yeah, another way is to have it come in here and just kick that off. Now we can't have it bond and just be there, but you can come in and kick it off. We've done that before. You need to look back at the handout I sent. There's two ways to make bonds. Carbocation. How do you attack carbocation? Anybody remember yet? Either side. Okay? What if you attack and kick off a leaving group? How do you attack? Backside. Yes. Okay? What does this arrow movement give?
Just that.
Gives that. Doesn't it? Lone pair now bonded here. Lone pair now bonded there. What does this generate? Everything is now there. How many intermediates did we form? Not here. If we do a reaction coordinate diagram, we start here. Any intermediates? No. We end up here. How do we get there? Some transition state. Right? This is our transition state. I mean, anytime. What is this right here? That's a transition state that's formed leading to this. What's that right there? Transition state leading to this. It's just these humps have different levels of where you're going. This hump is going relatively the same energy, but this is your activation energy, right? Here you go. Okay, which step is the rate determining step? Well, there's only one. So which one is the rate determining step? That one. That one. That's the rate determining step. Okay, how many of the reactants are involved in that step? Both of them. That's called an SN2. Is this mechanism different from the one above? Yeah, look at them. They're different. Okay, gotta be careful. SN2 only involves one step. This one only does. And yes, the substitution, SN2 only involves one step, the substitution part. There may be activation steps though, we haven't got to that yet. Where typically SN1 involves what? Ionization, then attack carbocation. Now if we had stereochemistry here, what type of stereochemistry would take place here? Backside attack would give, I don't think we used the term. We'll get the stereochemistry. It's going to be just like on that handout from a month ago. Okay? Now, which mechanism do you like best for this example reaction? SN1 or SN2? SN2. Why do you like SN2 better? Main reason because the SN1 would involve a primary carbocation, and typically you do not want to form primary carbocations unless you have to, and usually you don't have to. Primary carbocation is bad. Secondary is okay. Which is going to be the best? Tertiary. Which is better, tertiary with no resonance or tertiary with resonance? Yeah. All comes together, yeah? Yeah, the model reaction is a classical SN2 reaction. Okay? Mainly because the halide is on a primary carbon, also called a primary halide. don't want it to ionize and make a primary carbocation. That's not a good group. Okay? But I showed you both. We discussed them in context with each other, and I think it's a better way to quickly compare. Avoids tunnel vision. Proving, determining mechanism. We kind of already did that by looking at rate determining steps. Now we can go back. How do you do kinetics or whatnot? Okay, studies have shown that the rate of that reaction up there can be affected by changing the concentration of either the alkyl bromide or the hydroxide. Thus, the rate depends on both of the substrates. Because if you can change either and the rate changes, that means the rate depends on both. Since the rate depends on both, each must be involved in the rate determining step. What does that tell you that the mechanism is? We've already answered it. SN2, because both are involved in the rate determining step. We can tell that from mechanism, but how can you tell that in lab? Well, you do the reaction, you get a rate. Okay, we haven't learned how to determine rates. Then you do the reaction again, where you have changed the concentration of this. The rate changes, that means this is affecting the rate. The only way it's going to affect the rate is if it's involved in the rate determining step. Then you change the concentration of the hydroxide. If that changes the rate, that tells you the hydroxide must be involved. What if you change the grade of the hydroxide and the rate doesn't change? That tells you it's not involved. Since both of them changes in either changes the rate, that tells you it's SN2. But we've already explained mechanistically that it's SN2, so that all fits. I did it backwards. Sometimes I say this first and then I show that. Okay? Now, rate equation is SN2. Okay? Just like you learned in Gen Chem, the rate is going to equal some type of constant, K, times the substrates that are involved in the rate determining step. Since it's SN2, they're both involved. So it's time the concentration of your alkyl bromide, which is the substrate for the leaving group, times the concentration of the hydroxide, which is your nucleophile. If this was SN1, what would the rate equation look like? Or what would be different?
Get rid of the hydroxide.
Yes, you would get rid of that because it doesn't affect the rate. It would just be that. Now, built into this constant are lots of things, like the fact that it's a primary halide or whatever. This constant can vary, but that's a huge thing there. But it is some constant for any given reaction. Now, the rate units can actually vary. Back in Gen Chem, here it's actually going to be molarity per second for an SN2. But when you did all that rate stuff back in Gen Chem, the units for rate can actually vary, right? Okay, we've already did a reaction coordinate diagram for both. So let's look at the reaction over here. This reaction is a little bit different, and it includes stereochemistry. You take this alkyl bromide, which is R, reacting with KOH. You can get this alcohol plus KBr. Note that I am showing the spectator ions. Potassium, just a spectator ion. This is really hydroxide. This is Br minus. This reaction is known to give complete inversion of stereochemistry. Inversion, that is, we start with R, now we have S. Only S. It has inverted terminology. Before we look at the stereochemistry, and we'll end here, you can look at these on your own. We'll pick it up here. First, is an SN1 mechanism more or less likely favored for these? answer on Monday. Then, which mechanism of the two does the stereochemical outcome support? Why is inversion obtained? We will look at a 5-coordinate transition state, but not a 5-coordinate intermediate that is actually a true intermediate. Please look ahead, guys, okay? We'll move through this stuff. See some of you this afternoon.